Digital electronics. The band theory of solids explains how digital electronics work. It gets pretty heavy stuff here, but it's very interesting to read. Then some practical things: semiconductors and doping, semiconductor diodes, transistors, analog and digital circuits, and winding up with logic gates. Band theory of solids. The energy band concept was first introduced in 1928 by the Swiss-American physicist Felix Bloch. It helped explain many properties of solids by using quantum mechanics. Quantum mechanics depends on the wave function. The wave function, also written as psi, describes all the measurable quantities of a system. When it is squared, it tells you the probability of finding a particle in a particular position. Consider the hydrogen atom that has one electron. The wave function of this system can be either positive or negative. Both are valid solutions of the Schrödinger equation. The Schrödinger equation explains how a quantum system changes over time. When two hydrogen atoms are separated by a large distance, they have no impact on each other, and each atom has an energy level scheme that depends only on its wave function. As they approach and get closer together, their individual wave functions overlap and they add together. When you have two positive or two negative wave functions add together, their sum is a non-zero value. The probability of finding the electron in an energy level is the square of the wave functions and is non-zero. But what if a negative wave function of one atom is added to the positive wave function of the other? Then the sum will be zero and the electron can't be found in certain places. Since the combined wave functions are different depending on whether they sum to zero or a non-zero value, the system has a different energy. There are now two different wave functions caused by this overlap, splitting the original energy level into two levels. We have a graph now. Here's the atomic separation of our two hydrogen atoms, and here's the energy level, the various different energy levels. The right side of the graph shows the 1s and the 2s orbital for individual hydrogen atoms that do not interact. They're too far away from each other. See the atomic separation? They're way far away from each other. As they get closer, the two hydrogen atoms bond together to form H2, a new system. We now have overlapping wave functions that will split the 1s and the 2s orbitals into two energy levels each. So the 1s now, for the combined hydrogens, you have two energy levels there instead of just the independent one when you had one atom. And over here, 2s, you have two energy levels where you used to have one. Now consider four atoms coming close together and forming a solid. It follows the same concept as the two hydrogens coming together to form H2. This time, each energy level splits into four new energy levels. Four atoms, four new energy levels, four new ones for the 2s, and four new ones for the 1s orbital. Now let's keep increasing the number of atoms. For a very large number of atoms that come together to form a solid, there will be so many new energy levels that the difference between the levels will be very small. The energy levels will be so close together that they look continuous, and that's what's called the energy band, this light blue color. The nature of energy bands determines whether the material is a conductor, insulator, or semiconductor. In a conductor, the electrons are free to move throughout the material in response to an applied electric field. That enables them to conduct electricity. Insulators do not have enough electrons that are free to move. They are bound to the atom. Electric currents will not flow easily, if at all, through insulators. And finally, we have semiconductors. They are between conductors and insulators in their ability to carry current. And the band theory of solids that we just went through explains this behavior, and now we'll show more details on it. We're going to show two bands here, the conduction band and the filled valence band. And a few slides before this, remember the energy bands, you had the 1s or the 2s split like this, and then over here is all the different energy levels. That's what we're showing here now, with increased energy going up that way. The highest band that is full of electrons is called the valence band. The next higher energy band is called the conduction band. These two bands are separated by a forbidden energy gap, E sub g. Depending on the type of material, electrons may be able to move into the conduction band from the valence band. In a good conductor, such as a metal, there is no energy gap, and the filled valence band, and that goes like this, overlaps with the conduction band that comes down here. And the overlap between the bands is shown in that green color. Electrons, even at absolute zero, can occupy the top of the filled valence band up to the red line in the diagram. That's right over there. You know what? Let me erase that so you can see that better. There we go. They can easily gain small amounts of energy in response to an applied electric field. Therefore, these electrons will be mobile, and they give the conductors their high electrical conductivity. For insulators, there's a very large energy gap between the valence band and the conduction band. The valence band is completely filled, and the conduction band is completely empty. So empty, filled. At room temperature, the energy gap is about 5 to 10 eV electron volts. The average kinetic energy of electrons at this temperature is 0.05 electron volts. Even with an external electric field, electrons cannot reach the conduction band as they don't have enough energy. So, the result is electrons are not free to move through material, so conductors have a very low electrical conductivity. The energy bands of pure or intrinsic semiconductors, here you go here, and here you go here, are similar to those of insulators, except that the empty conduction band is separated from the filled valence band by a much smaller energy gap. Much smaller gap here. That's on the order of 1 electron volt. At room temperature, only a few electrons can acquire enough thermal energy to reach the conduction band. Only a small current can flow when an external electric field is applied. At higher temperatures, more electrons have enough energy to move up to the conduction band, so their ability to conduct electricity increases. This temperature dependence is opposite to the behavior of conductors, where their conductivity decreases with increasing temperature.